Hello everybody, this is Gerhard Steiner from GRIMM Aerosol Technik. Today I'm going to show you our final setup of a mobility particle size spectrometer that's able to access the 1 nanometer size range. We call it the PSMPS. First, you may ask, 1 nanometer particles, where do you actually find those? Well, for example, in the atmosphere, there are primary ions or neutral molecules that can combine with each other to form stable molecular clusters by the process of nucleation or new particle formation. And those clusters are in the size range between 1 and 2 nanometer. They can grow further by condensational growth to even larger clusters, but that's a game about life and death because they can be easily scavenged by already pre-existing aerosol and thereby being lost. Eventually, some of them will survive and grow further to larger particles, for example, to cloud condensation nuclei in the size between 50 and 100 nanometer. So what we have is a conversion of trace gases or VOCs into the particle phase, where the understanding of the basic mechanisms in the 1 to 2 nanometer size range is important to understand the overall process. The final PSMPS setup that is thought to access this size range comprises a modified GRIMM S-DMA, the short one, a new model of CPC, the 5417, with an integrated DMA controller and also an integrated sheath air supply for the DMA. Then there is the Airmodus PSM that enables us to detect those tiny particles and clusters. It draws a sample flow through the DMA of 2.5 liters a minute and passes a flow of 0.6 liters per minute to the CPC. CPC and PSM are connected to a computer where a data acquisition and controlling software is running. Important for the operation of the overall setup is a newly designed core sampling inlet probe. I will speak about that more in a minute. And also a aerosol neutralizer, in this case a nickel-63 source, to bring the aerosol under investigation into a defined charging state. I would like to go step by step through all the individual components and to show you what progress we made since last year and where the differences are. First, the modified GRIMM S-DMA. In fact, it's not that much different to the standard GRIMM S-DMA. The geometric dimensions are the same. Also, the channel length is the same of 50 millimeters, but it has got an optimized aerosol in and outlet port, which is thought to reduce diffusion losses of especially the smallest particles there. It can be operated with a positive or negative voltage on the center electrode between 5 and 10,000 volts. And if it's operated at a sheath flow of 10 liters per minute, it has an accessible size range between 1.1 and 55.7 nanometer. We checked the size-dependent penetration of particles through the modified DMA and compared it to the standard DMA. On the vertical axis, the DMA penetration. On the horizontal axis, the particle diameter. Blue dots are experimental data for the standard DMA and red dots experimental data for the modified DMA. And the solid lines show a laminar diffusion deposition model fitted to the data. What we found for the modified DMA is an improved penetration for the particles of a factor of 6 at a size of 1.6 nanometer. It's improved by a factor of 2 at 2 nanometer and improved by 40% at 3 nanometer. The Airmodus A-10 PSM is a mixing type instrument where a clean airflow of 1 liter per minute, in our case, saturated with diethylene glycol vapor, is mixed with the sample air. Particles grow in a growth tube to sizes of about 100 nanometer and are passed on to a CPC for the actual detection. And we can determine, of course, a overall counting efficiency of a PSM together with the counting CPC, the 5417. What we found for these operating conditions is a quite satisfying performance with a counting efficiency close to 1, so close to 100% as a plateau value from particles starting at 4 nanometer down to 2 nanometer, even a little bit below 2 nanometer, and is then steeply decreasing with a D50 cutoff diameter of 1.6 nanometer in this case. The GRIMM 5417 CPC is a modified version of a CPC we already had, but updated with additional features. It has an integrated DMA controller and a sheath air supply for 2 sheath air flows of 3 and 10 liters per minute. Those flows are controlled by temperature stabilized critical orifices, and you can decide either 3 or 10 liters per minute by manually exchangeable critical orifices. There is also the option of 2 inlet flows of 0.3 and 0.6 liters per minute. Those flows can be switched by the user software. The sheath air loop also includes a sheath air drying unit. That's important to reduce humidity effects, especially on the performance of the particle size magnifier. Something very important for a good operation of the system is the newly designed core sampling probe inlet system. It's based on the paper by Fu et al. In Aerosol Science and Technology from last year. There they made a theoretical and experimental analysis of the core sampling method. We followed their script. They also published in the supplemental to their paper and designed a probe with these geometric dimensions. We use a sample flow rate of 2.5 liters a minute, a transport flow of 7.5 liters a minute, which sums up to a total flow of 10 liters a minute. And if we use flow rates with the given geometry dimensions, we can calculate with the script published by them in their supplemental a sampling efficiency dependent on the particle diameter, and it gives us again quite satisfying performance down to 1.1 nanometer, where the limit of our accessible size range is, and this is then also steeply decreasing with further particle decrease. The charge conditioning unit is a nickel 63 aerosol neutralizer. It's a beta minus radioactive source with an activity of 95 megabecquerel. I'm just mentioning this here because using those nickel 63 chargers is quite handy, because there is most likely no handling license needed, because they are typically below the radionuclide specific exemption limit, which is at 100 megabecquerel. And if you use just one of those, no handling licenses or whatsoever are needed to operate those. To give you an idea how the final setup looks like in real life, on the very left, the Airmodus PSM on the bottom, with the directly connected DMA at its inlet. This was another motivation for the redesign of the DMA, to be able to place it directly at the inlet. There is the sheath air drying column, there is the CPC on top of it. You see, it's quite a handy, compact setup of instruments. On the very right-hand side, you see a close-up of the directly connected DMA directly in front of the PSM. On the back of the PSM, the size magnified particles exit the instrument, are then further led to the inlet to the CPC for the final detection. We are happy that we are able to currently run a field campaign together with the DWD, the German Meteorological Service, at their observatory at Hohenpeißenberg, which is in the south of Germany, south of Bavaria. It's southwest of Munich. Many thanks to Gerhard at this point to make this possible, that we are using their facilities there. The campaign has just started a couple of weeks ago, 2 weeks ago, on August the 17th. But to show you how this looks like in a real life setup at the lab, with all the cables and all the tubings. On the left, this typical setup with the PSM on the bottom and the other instruments on top of it. On the picture in the middle it shows the rear panel of the CPC and also the controlling computer with the data acquisition software. And on the right hand side there is the core sampling inlet connected to the nickel 63 charger that's also connected to the modified DMA in front of the PSM. Luckily enough, we are already able to show some preliminary data from those measurements. Here, size spectra from midnight to midnight, from Tuesday, August 18th. So this is the second day of measurement. What we found there already are quite short time but fast happening nucleation bursts, evolving from the 2 to 3 nanometer sizes. What we also see here at 8 o'clock in the evening are nucleation events followed by some growth events. In addition to what we see is this red band. This is originating from the signal from the ions coming from the aerosol charger. So those are the charger ions. Still, this is very preliminary data, and we need to do more thorough data analysis throughout the campaign and also post-processing of the campaign, but the data looks very, very promising already from now on. To sum up, what I have shown you is our final PSMPS setup with the new modified DMA and CPC. I've shown you the performance of the individual components like the core sampling probe or the DMA, and I was able to show you some preliminary data of our currently running campaign at home Peisenberg together with the German Meteorological Service. Thank you very much for your attention, and I'm happy to answer your questions.